So, you know that old saying, when life gives you lemons? Well, forget lemonade. Today, we're going to use them to dive into electricity and, yeah, even a little bit of quantum physics. Let's get into how this simple little fruit can pull off something so incredible.
I mean, it really does seem like a magic trick, right? You stick a couple of pieces of metal into a lemon, and boom, an LED lights up. But what's really going on behind the curtain? How can a piece of fruit possibly generate power for modern tech? That's the big question we're going to unpack right now. So, first things first, we've got to understand the power that's just hiding inside the lemon. And to do that, we have to start with the absolute basics. Okay, so at its core, electricity is really just a flow of these super tiny particles called electrons. Now, the secret to any battery, I don't care if it's in your phone or it's a lemon, is creating this, well, it's like a chemical disagreement. You've got one material that's just dying to get rid of its electrons and another one that's desperate to grab them. That whole push and pull is what gets everything moving. So who are the main characters in this little chemical dance happening inside the lemon? Let's zoom way in, down to the microscopic level, and see what's actually going on in that acidic juice. All right, here are our two key players. On one side, you've got the zinc that's coating the nail. Now, zinc is super generous with its electrons. It really wants to give them away. And on the other side, we've got the lemon juice, which is packed with hydrogen ions. And these guys are eager to gain electrons. See? It's this fundamental conflict, this desire to lose versus the desire to gain. That's the real engine of our battery.
So here's how it goes down step by step. A zinc atom, just chilling on the surface of the nail, decides to give up two of its electrons. The second it does that, poof, it's not a stable piece of metal anymore. It becomes a positively charged zinc ion and just dissolves right into the lemon juice. So now you've got these two freed up electrons, and they need a new home. They find some hydrogen ions hanging out in the juice, which snap them right up and turn into bubbles of hydrogen gas. And, if you actually let this run for a while, you could see those tiny bubbles forming on the nail. It's pretty cool.
Okay, but hold on a second. If this whole reaction is happening right at the nail, why do we even need the copper wire and the pennies? Well, it turns out there's a microscopic traffic jam we have to solve. And the solution? It reveals something totally fascinating about how electricity really works.
So here's the gridlock. As those positive zinc ions float away from the nail, they create this little cloud of positive charge right around it. And this cloud acts like a roadblock. It starts pushing away all the other positive hydrogen ions that are trying to get to the nail to pick up electrons. The whole system would just seize up, almost instantly. And this is where the design is just brilliant. That copper wire, it's like a dedicated superhighway, an express lane just for the electrons. It gives them a totally clear path to get away from the traffic jam at the zinc nail and drive all the way over to the copper penny. Over there, they can meet up with hydrogen ions in a different part of the lemon, no problem. It's basically building an overpass to get around downtown traffic. It keeps everything moving.
Okay, so we've got this electron superhighway. Electrons are flowing, but let me ask you something. How fast do you think a single individual electron is actually moving down that wire? Are we talking like close to the speed of light? What do you think?
Get ready for this, because it's going to blow your mind. The actual speed of one of those electrons is about 33 nanometers per second. I mean, that is ridiculously, laughably slow. At that speed, it would take an electron almost an entire week just across the tiny little distance of the LED. So how in the world does the light turn on instantly? The answer is all about the difference between the particle itself and the signal. Think about a really long line of dominoes, right? When you push that first one, the very last one falls almost instantly. The force, that ripple, travels super fast. But each individual domino, it barely moves from its spot. It's the exact same thing with electrons. The push, that electrical signal, zips through at nearly the speed of light, kicking the whole chain reaction off at once. So while each electron is just kind of shuffling along, the sheer number of them on the move all at once is just staggering. At any single point in that wire, you've got 9 quadrillion, that's a 9 with 15 zeros, electrons flowing past every single second. And that massive collective movement is what we actually measure as the electrical current. All right, so we've figured out how to create a flow of electrons. Awesome, but that's only half the journey. Now we have to figure out the destination, the LED itself. And to really get how that works, we need to take a little side trip into the very strange world of quantum physics. So let's imagine the inside of an LED is like a special kind of road. It's made from two different materials, we'll just call them N and P, and this road has two very important rules. First, it's a one-way street. Electrons can only go from the N side to the P side. And second, the road isn't flat. The p side is actually uphill from the n side.
Now, as you probably know, electrons are, well, they're kind of lazy. They are not going to go uphill by themselves. They need a push. And that push, that's what we call voltage. It's the amount of energy we give them to make that climb. So in our little analogy here, the voltage from our lemon battery is what's lifting the electrons high enough to get them over that hill, from the n side to the p side.
But there's a catch, and it's a quantum catch. The N material is super picky about energy. Electrons can only exist at very specific, separate energy levels. Think of it like an elevator that can only stop at floor 1 or floor 2, but never, ever in between. You can't just give an electron a tiny bit of energy. You have to give it enough of a boost to make the full jump to the next allowed floor. And this right here is exactly why one lemon won't light the LED. We need the combined voltage from 3 lemons to give those electrons enough of a lift to reach that next required energy level.
Okay, so we've used our 3 lemons. We've lifted the electrons up to the energy level they need to be at. They've traveled across that one-way street. And now comes the magic, the payoff for this whole crazy journey.
So here it is, the moment of creation. An electron gets boosted up to a high-energy floor on the N side. It crosses over to the P side. But on the P side, the only available floor is way down at a much lower energy level. So what does the electron have to do? It has to drop. And as it falls, that extra energy it had has to go somewhere. It gets released, not as heat, not as sound, but by creating a single tiny particle of pure light, a photon. This amazing process, it's called electroluminescence. And the coolest part is we can control what that light looks like. The color, that's all about how big that energy drop is. A really big drop releases a lot of energy, giving you a high-energy light like blue or violet. A smaller drop, you get red or orange. And the brightness? Well, that's just a numbers game. The more electrons you have flowing through, the more photons get created every second, and the brighter the light gets. Simple as that. So we've gone from a chemical reaction inside a lemon all the way to the birth of a photon of light. It's pretty incredible. So now let's just zoom all the way back out and appreciate how this simple little kitchen experiment connects to, well, pretty much the entire modern world.
I mean, this principle isn't just a fun party trick. It is, and I mean this literally, everywhere. It's in the screen you're probably watching this on right now. It's in our TVs, our computer monitors, the light bulbs that light up our homes. The humble little LED has completely changed the game for modern lighting and display tech.
And it goes even deeper than that. This exact same interaction, this dance between N and P materials, it's not just for making light. It is the fundamental building block of every single transistor, every microchip, every computer processor on the planet. The science behind this simple experiment is the very bedrock of all modern computing. This is Nobel Prize-winning stuff, folks, pioneered by giants like Albert Einstein, who actually won his prize for explaining a very similar quantum effect.
So, from a lemon in your kitchen to the foundations of modern computing, it really makes you wonder, doesn't it? What other simple, everyday objects are sitting around us right now, hiding equally profound, world-changing science, just waiting for us to take a closer look?